So today we'll begin chapter 15, which is probability. Have you ever wondered what are your chances of winning a jackpot? Or can you predict the chances of seeing rain today or not? Well, the answers to all these questions can be provided to you if you understand probability. So, if I ask you to tell me what is 2 plus 2, your answer would be 4, right? And if I give you 2 into 3, your answer will be 6. So can you say that these statements are true for sure? Yes, you can. But when we talk about the real world, then there is not that much of certainty. And hence we introduce the concept of probability, which is an important part of applied mathematics. Now, what is probability? Probability is a measure of how likely something can take place. So, this probability can be of two types. It can be empirical or it can be theoretical. Now, empirical probability is also called by the name of experimental probability. In fact, empirical itself means experimental. And theoretical probability is also called your classical probability. So now what do we mean by these? How do we deal with them? All of this we'll see in the coming few minutes. So experimental or empirical probabilities, as the name suggests, refers to finding probability based on actual experiments. So you perform an experiment, you jot down your observations, and on the basis of that, you predict the occurrence of further events. But all these probabilities are estimates. You should be very careful of this point. So if I say that there is a 50% chance of raining tonight, then it means that it can rain, but it cannot rain. So sometimes things can happen, against the probabilities as well. So they're just estimates to just give you a rough idea as to how likely something can happen. Now, before we move on to the details of probabilities, there are a few terms associated with probability which I would like you to get acquainted with. So, number one, events. So, whatever trial or experiment you are performing in probability is called an event. So, for example, we consider this case of tossing a coin. So, when we toss a coin, we can expect two results, heads or tails. So now this is an experiment. So tossing a coin is an experiment or it is an event. Okay, can you think of other events? So other events can be rolling dice. It could be drawing a card from a deck of cards. In fact, it could be anything. So all these experiments or trials are called events in probability. Number two, here we'll often use the term likely or unlikely. So very rarely it happens in the real world that we can be absolutely certain about something. So we prefer using terms like this event is more likely to take place or this event is unlikely to happen. So it's not 100%, as I just stated, they are all estimates. So you provide the likelihood of an event taking place. Then if you've understood this, let's move on to theoretical probability. So theoretical probability is based on assumptions. So here you do not perform these events or these trials or your experiments, but here just you theoretically study probability and then you make some estimations. Okay, so what is the difference between experimental and theoretical probability? That the former, your experimental probability is based on actual experiments and theoretical probability is based on assumptions. Now, whenever we deal with a particular problem, which probability do we consider? So we can consider either of them. And what is noticed is that if you repeat an experiment several times, then in fact experimental probabilities and theoretical probabilities are in sync with each other. So they give you the same results then. Okay, so what you were expecting theoretically turns out to be true experimentally also, provided you perform that event several times. So for example, if you toss a coin, say 1,000, 10,000 times, then your expectations from these events, that the probabilities would be 1/2 each for heads and tails, would actually turn out to be true. So this is the formula for experimental or empirical probability. It is very important to notice how we denote probability. So P stands for probability, and here the parentheses which are shown here, basically your round brackets. Inside these parentheses you mention the event. Okay, you can have an event name by yourself. So we denote them by capital letters usually. You can use any letters of the English alphabet ranging from A to Z, or you can write this event in words as well. It doesn't matter. So since it's experimental, here we obtain these probabilities by performing an experiment, also called an event or a trial. So hence the formula goes by P of E is equal to number of trials in which the event happened. The event happened. So it means that the event that you're looking for. So for example, if you're tossing a coin, say you're looking for a heads. So the number of trials in which you got heads in that case upon total number of trials that you performed. Okay. So if you're tossing a coin, then number of times you tossed the coin would come in the denominator, and the number of times you got heads would come in the numerator. The ratio would give you the probability of getting a heads. So we can actually use this empirical probability in different experiments then to make estimates. Then what is the need for theoretical probability if we are good to go with experimental probability? Well, experimental probability works really well as long as you just have to perform a few attempts, okay? But if I ask you to perform an experiment, say 10,000 times or 24,000 times, that wouldn't be that feasible for you. Plus, it wouldn't be cost effective. That would be very laborious, expensive, and also not possible several times. So due to this limitation of experimental probability, we switch to theoretical probability. Anyways, it's very easy. You just need to make use of your assumptions and logical knowledge and then make predictions, which we would also do in today's class. So the good thing is that if an experimental probability is taken, it will actually turn out to be, your experimental probability will turn out to be equal to theoretical probability if in real life you perform that experiment several times. So if experiment is performed several times, then experimental and theoretical probabilities become nearly equal. Now you only tell me, so for example, we are launching a satellite, okay, and we need to see, we need to make a prediction if the satellite would be successful or would it be a fail. So how would you predict it? Obviously, theoretically, you can't attempt to launch a satellite 1,000 times. That would be so cost effective. You can't burn a hole in your pocket, right? Then, for instance, you want to see that there's a multi-storied building, okay? And you want to see that will it be able to survive the tremors of an earthquake or would it collapse? So obviously you won't wait for your building to get into a dilapidated condition, in order to make out if it's going to be experimentally correct or not, probability wise. So these things are not feasible. So that's why there's a dire need in fact for theoretical probability, and that's why we're studying it. Okay, so there are some common terms in probability. So here we often make use of the term unbiased and biased. So as the name suggests, unbiased means fair, as in just, and biased means that it's unfair, okay, it's not just. So what do we mean by this? So let me explain it to you by means of a fun activity. So take any coin. So any coin would have heads and tails. Those are the two sides of a coin, right? And let's say you're playing with your friend, and you'll see that the person who wins would be the one who is getting a heads on the coin while you flip the coin. So if you flip a coin, you can get two possibilities here, right? So this is an unbiased coin, okay? This coin is fair, okay? So both the outcomes are equally likely. You can get a heads, you can get a tails. But let's say your friend decides to cheat. What he or she does is that person takes the coin, has heads on one side already, and he or she tries to cheat by making the other side also heads. So when he or she would flip the coin, 100% that person is going to get heads and that person will win. So is that fair? It's not fair. So that's what we call a biased coin. Alright. So in this chapter though, we'll be mainly restricted to unbiased cases. So these are the possibilities. Okay, so just to acquaint you with the terms unbiased and biased in probability, I just took up this example. So these events, if you see here, heads or tails, by knowledge of a basic probability, you know that whenever you flip a coin, there are two possibilities, heads or tails. So there's equal chance of the occurrence of both the events, or I can say 50% chance of heads and 50% chance of tails. So such events are said to be equally likely. Okay, here you can't say that getting a heads is more likely than getting a tails. You can't say that this is more likely or this is less likely. Here it's the case of equally likely events. So then what is the formula for classical or theoretical probability? So we are studying this because experimental probability also approaches this value of theoretical probability if an experiment is performed several times. So again, we denoted by P of E, and here instead of saying number of trials, because you're not actually performing those experiments, you say number of favorable outcomes favorable to the event E upon number of possible outcomes. Okay, so for example, let me repeat this case here of heads and tails. So I have a coin. What are the two possibilities? Heads and tails. So here you tell me what are the total number of possible outcomes. Obviously 2. So, and what are those two outcomes? Heads and tails. You can just mention them as well. Okay, then apart from that, you tell me number of favorable outcomes, and here by favorable I mean that let's say my event E is there. Let E be the event heads. Okay, so E is the event that you get a heads. So what are the favorable outcomes? There's only one favorable outcome. Okay, you can just get one head then. So then what will be the probability of this event E of getting a head? It will be number of favorable outcomes 1 upon total number of possible outcomes 2. So this is the probability of getting a heads. Now this is homework for you. You would predict the probability of getting a tails in the exact same manner. Note that the number of possible outcomes would still be the same. Now you need to see if number of favorable outcomes would be 1 or would it change, and then tell me the probability of getting a tails. Now, I would also like to tell you about probability lines that you can even get to know if you're going somewhere wrong in your answer, in your solution. So there is this probability line. You can note down this somewhere. It's very important according to me. So this probability line actually is like your number line. Okay, so it ranges from 0 to 1. So it's not like your conventional number line which ranges from minus infinity to plus infinity. Here it ranges from 0 to 1. We are restricted to this range. And what comes between 0 and 1? We get 1 by 2. Now here 0 means that the probability is equal to 0. So probability equal to 0 means that the event is impossible. Okay, impossible. We can say this with certainty that this event is impossible. And if I say probability is equal to 1, it means for sure. So certainly this event is going to happen. So it's not much of a question, dealing with probability, because here there are just 0% chances of the event taking place, and here there are 100% chances. So we can write these numbers in terms of percentages as well. So this is basically 0% chances, and this means 100% chance. So if you have probability coming in between 0 and 1 by 2, it means that the event is unlikely to take place or less likely to take place. And if it is between 1 by 2 and 1, the probability then the event is likely to take place. Okay, so this is the probability line. So with this you get to know that if your answer does not lie in the range of 0 to 1, it means you've done some mistake in your solution. You've gone somewhere wrong, and with this you can even predict that if the value is turning out to be between 1 by 2 and 1, that means this event is likely to take place, and if it's between 0 and 1 by 2, it's unlikely to take place. So 1 by 2 in fractions can be written as 50%. So just multiply all these numbers by 100 and you'll get the answer in percent. So now we'll understand the applications of probability via several examples. It's going to be a lot of fun. So find the probability of getting a head when a coin is tossed once, and find the probability of getting a tail. Well, you've already done this question, so let's have a quick revision now. It won't take much time. So I'll just tell you how to write your solution now properly. So you can say, on tossing a coin, number of possible outcomes. So we'll go step by step, okay, so that your answer is easily understood even by a layman. So number of possible outcomes would be 2. Those two outcomes would be heads and tails. Then you have to find out the probability of getting a head. That would be what? Number of favorable outcomes. Number of favorable outcomes here would mean the number of times you can expect to get a head upon the number of possible outcomes. So there would be just one favorable outcome. What is that? That is just heads. So 1 upon 2. Then similarly, you can find out probability of getting a tail. Use the same formula here, number of favorable outcomes to getting a tail upon number of possible outcomes. And you would notice that if you are going to get a tail, that also will be only 1 in number, and the number of possible outcomes would be 2. So here we see that probability of getting a head and tail is the same. That's why we say that when we toss a coin, the two events, getting a heads and getting a tails, is equally likely. So we say the two events are equally likely. Now here I'd like to introduce to you a new concept, which is that of elementary events. By now you already know what events mean, right? Experiments or your trials. So what do we mean by elementary events? Now elementary refers to something very basic, okay, if you go by normal English. But here in math and probability especially, elementary events refer to events with only one outcome. Please note down this definition. So events which yield only one outcome are called elementary events. So in this case, if we see the event getting a head, then that is an elementary event. Why? Because here there is only one outcome, which is heads. That's why we write a 1 here. Similarly, can you say the same thing for tails as well? Is this event an elementary event or not? Well, even this is an elementary event, because when you toss a coin once, you can get only one tail. That makes it as one outcome, and hence this is an elementary event. Now, what is so special about these elementary events? So, sum of probabilities of elementary events associated with one experiment. Okay, like here the experiment was tossing a coin once. Associated with one experiment is equal to 1. So basically, if you sum up the probabilities, just do it for me. Probability of getting a head and probability of getting a tail. What would that be? 1 by 2 plus 1 by 2, that will be 1. Don't be surprised, because you'll always get that as 1 if you take up the sum of elementary events associated with one particular experiment, which in this case was tossing a coin once. Now we have example 2. So here we are having a bag. So let's make a bag. Okay, and here we have a red ball. So we have a red ball. Then we have a blue ball. And we have a yellow ball. So just a pop of colors in this question. Alright, so we are having these 3 balls in a bag, right? So all these balls are of the same size, and there's a girl, Kritika, who takes out a ball from the bag without looking into it. So if she does not look into the bag, that means there's the equal chances of getting any of these outcomes, okay, red, blue or yellow ball. So what is the probability that she gets a yellow ball or red ball or a blue ball? So for that, let's first of all see number of possible outcomes. So number of possible outcomes would be 3. How would they be 3? Tell me. Just think a bit about it. There are 3 possibilities. You can get a red ball, or you can get a yellow ball, or you can get a blue ball. So there are 3 possible outcomes. Now let me name these events. So let the events be. How many events are there though? We are discussing 3 events here: yellow ball, red ball and blue ball. So let me have Y for yellow, R for red, B for blue. So this is the event for getting a yellow ball, this is the event for getting a red ball, and this is the event for getting a blue ball. Alright, now we are ready to take up the final question here. So first part is probability of getting a yellow ball. That means P of Y. Okay, so to get this, you need to know number of favorable outcomes. That means the number of times you can expect to get a yellow ball. So how many times can you expect to get a yellow ball? Since there is only one yellow ball, you'll have 1 upon total number of possible outcomes is 3. So here also you can write the full formula that probability is equal to number of favorable outcomes upon number of possible outcomes. So there are 3 balls, hence 3 possible outcomes. And talking about the favorable outcomes, that means number of times you can get yellow, that will be just 1, because only 1 yellow ball. You can see that colorful bag here, you're just having 1 yellow ball. In a similar fashion, I want you to do the next 2 parts and then verify your solution with me. So since bag has only 1 red ball, therefore probability of getting a red ball denoted by PR is equal to number of favorable outcomes, that is 1, because there's only 1 red ball. So there's only 1 favorable outcome upon total number of possible outcomes, which would be 3 because there are 3 balls in the bag. Third part, now your bag has only 1 blue ball. Therefore PB, which is probability of getting a blue ball, will be 1 because there's only 1 blue ball, so 1 favorable outcome upon number of possible outcomes would be 3 because the bag has 3 balls. So if you notice here, your PY was also 1 by 3, PR is also 1 by 3, PB is also 1 by 3. Now I already told you what are elementary events, so tell me what are they? So those are the events which give you only 1 outcome. Now in this question, when Kritika draws a yellow ball from the bag, can you say that it is an elementary event? Yes, it is an elementary event because there is only 1 yellow ball. So there was only 1 possible outcome, right? 1 possible favorable outcome. Talking about a red ball, there's only 1 red ball, so there's only 1 favorable outcome. So this is also an elementary event. And the same can be said true for the blue ball. So all 3 are elementary events because all of them yield you only 1 outcome. So I told you that if you add up all these probabilities for elementary events associated with an experiment, which was taking out a ball from the bag, then they'll turn out to be, the sum would turn out to be 1. So let's check that. So just do PY plus PR plus PB. So it will be 1 by 3 plus 1 by 3 plus 1 by 3. That makes it 3 by 3, that is 1. So hence we have verified that all these 3 events are elementary. Hence the probabilities associated with them when added up give you the sum as 1. So we've already discussed what are elementary events by means of examples. So an event having only 1 outcome is called elementary. Elementary means 1 or basic, okay, most basic usually. And what can you say about the sum of probabilities of all such events? Sum of probabilities of all elementary events of an experiment is 1. So when you toss the coin, you notice that P of getting a head and P of getting a tail. When you added them, you got 1 because this was also equal to 1 by 2 and this was also equal to 1 by 2. So both the events were equally likely as well because you're getting the same probability for them. Same can be said for the previous example as well, where for all the 3 balls, you were getting the same probability. So there also, getting a yellow ball from the bag, getting a blue ball and getting a red ball from the bag, all of them were equally likely because all had the same probability 1 by 3. And questions associated with probability, you can leave your answer in decimals or even in simplified reduced fractions. Okay. So then we have die. Now you must be wondering what does a die mean? So die is singular and when you do its plural, that is dice. So please don't get confused. So here even they have used a. So look at the article that they've used. Okay. So singular is die and dice is plural. So if I just give you one of them, then that is a die. If I give you more than one like 2, then that becomes dice. So you're rolling a die once. So you have to tell me the probability of getting a number greater than 4 or less than or equal to 4. So here, what are the possibilities when you roll a die? Have you ever played snakes and ladders or Ludo? You must be knowing then. So one possibility is that you get 1 on the die. Another possibility is that you get 2. Well, there is one more possibility, that is you get 3. Well, there is just one more, that is 4. Are there any more possibilities? Yes, there is a 5 here, like this, and there is a 6. So, if you have any board games in your place, and you gotta die, then quickly grab it and it will make it all the more interesting and fun. So there are 6 possibilities. If you can see, you can get a 1, 2, 3, 4 or 5 or 6. Okay, so number of possible outcomes in this case would be what? It would be 6. Okay, so now let me say for the first part, let E be the event getting a number greater than 4. Okay, I am using the symbol. You can write the entire thing as well if you wish to do so. Then what will be the favorable outcomes if you want to get a number greater than 4? What are the numbers greater than 4 on your die? They are 5 or 6. So these are the only 2 favorable outcomes. So favorable outcomes become 2 in number. So probability of E, which means getting a 4, a number greater than 4, would be number of favorable outcomes upon what comes in the denominator? Number of possible outcomes. So this symbol means I'm just copying what's stated above. Okay, so number of favorable outcomes would be 2, only 5 and 6. And what will be the total number of possible outcomes? 6. Why? Because you can get 1, 2, 3, 4, 5 or 6. So you can simplify this fraction. That will become 1 by 3 then. Okay, then let's take up the second part of this question. The probability of getting a number less than or equal to 4. So similarly, let me assume an event F, which is getting a number less than equal to 4. I can use this symbol then. So what will be the favorable outcomes? So if you just look at the symbol less than, it means you can have 1, 2, 3, 4. So on a die, you see that numbers start from 1. So you can have 1, 2, 3. Will I have 4 as well in this list? Yes, because there is an equal to symbol as well. Or in words also they have said equal to. So 1, 2, 3, 4. How many favorable outcomes are there? 4. So I'll solve it over here. So probability of F, which means getting a number less than equal to 4, will be number of favorable outcomes, which are 4 in this case, 1, 2, 3 and 4. And number of possible outcomes would be 6, numbers which are ranging from 1 to 6. Can we simplify this fraction? Yes. So this will become 2 by 3. So in this case also, if you notice, if you add the 2 probabilities, P of E and P of F, you are going to get 1 by 3 plus 2 by 3, that is 3 by 3. But are E and F elementary events? Then if the sum of probabilities is turning out to be 1, 3 by 3 is 1. But no, they are not elementary events, even though the sum of their probabilities is turning out to be 1 for the same experiment. But still we see that they are not elementary events. What makes me say so? Because elementary events are those that are categorized by only one outcome. But here if you notice, how many outcomes did we get? We got 2 outcomes. Here we got 4 of them. So neither is giving us just one outcome. So which means these events are not elementary. So it's just mere coincidence that the sum of their probabilities is turning out to be 1.